So as I said, we're going to be going through 4.7 today, and we're also going to go through 4.8. So 4.7 starts looking at these things called polymers. Okay, polymers are basically a molecule that's made up of many parts. Okay, and we've got two types. Okay, wait, about the test. Some of us have a math test just before that. Look, if you come a little bit late to the chemistry test, it's not a big deal. I'll just give you the extra time that you miss out. Okay. So yeah, when we're talking about different types of polymers, polymers means many parts. Okay, so poly meaning many, mono meaning one. So polymers are basically molecules that are made up of many parts, and the many little parts that make up a polymer are called monomers. Okay, so monomers, mono meaning one, are the single units, and the single units kind of combine together to form a polymer. Okay, polymer is basically like a constituent of plastic. Okay, so anything that's got plastic in it is made up of one or more polymers there. Okay, we've got three types of polymers. We've got linear polymers, elastomers, and crosslink polymers. Okay, linear polymers, as you can see, kind of follow a linear kind of shape there and structure. Okay, where the monomers kind of line up together. Elastomers are a little bit more flexible, so that's why we call them elastomers, like elastic. And cross-linked polymers are kind of like a mixture of the two. Okay, so that's basically what we're going through today. So when we look at linear polymers and elastomers, we have to remember that linear polymers form long chains, and they form kind of lines of those monomers, or lines of those little units there. Okay, those units are basically held together through covalent bonding. Okay, and the covalent bonding that occurs is one carbon atom covalently bonding with another carbon atom. So carbon is a nonmetal. So when those two bind together, they form a covalent bond. And that's what we see in our linear polymers. Okay, linear polymers are almost like always in a straight line. That's why we call them linear. Elastomers are a little bit different. They have elastic properties which make them more flexible. When we represent them in a diagram, they look kind of like a ladder, as you can see here. So they've got a ladder, and that ladder-like structure is because these kind of polymers, or these monomers that are basically combining together, kind of interconnect. Okay, they don't just go in a straight line, but they interconnect horizontally and vertically there. And so that's why they are more flexible as well. So if you ever think about a flexible plastic structure that you've come across, that would definitely have an elastomer in it, not a linear polymer. Okay, because elastomers have more elastic properties. For example, a rubber band. A rubber band is very flexible, it's very stretchy, and so that type of polymer that represents that is an elastomer. When we're looking at crosslink polymers form lattices. Lattices are basically like they overlap with one another. Okay, and as you can see, they form a very different shape from linear polymers and elastomers there. So they form giant covalent lattices. Okay, and basically, again, we're talking about carbon atoms here. But rather than having a very nice kind of organized arrangement, we see that these are represented in a kind of more kind of random structure or random kind of appearance there. Okay, we call it a haphazard arrangement because we don't have a straight line like we did in linear polymer. We don't have a nice ladder structure forming like we did in elastomers. It's very random. And essentially what happens is that these lattices form diamond-like structures, okay, within diamond-like appearances within the lattice. So you can see here that we can basically see that there's a formation of some diamond-like appearance and structures in that crosslink polymer there. Okay, so that's the basic idea. Again, we're still dealing with carbon atoms. So regardless of what polymer we're talking about, it's always the carbon atoms that are covalently bonding there. Okay, so just need to know one difference between the three. So linear polymers, elastomers, and crosslink polymers, literally just know the definition. We're not going to ask you to draw this. We're not going to ask you to, we're not going to ask you to unpack this. It's just a matter of knowing the difference between the three. It's a very theory-based topic, this one. Okay. In addition to that, when we talk about polymers, we can actually divide polymers into two broad categories. We can divide them into something called thermosetting polymers and then thermoplastic polymers. Thermosetting polymers are basically the main difference between thermosetting and thermoplastic polymers is that thermosetting polymers are polymers that basically, or plastics that basically cannot be melted. Once they've gotten their shape, or once they've been constructed, we can't go back and melt that, okay? They don't respond to heat very well. Thermoplastics, on the other hand, normally we say that we can melt plastics. So just think of it like that, okay? Thermoplastics are essentially plastics that once they're formed, you can go back and put these plastics under extreme heat and they can be melted repeatedly. So the Lego will melt and then it will reform under cold temperatures. Then we can melt it again and it will reform again. So that's basically what a thermoplastic is, okay? So polymers, because we usually classify polymers based on how they respond to heat, that is whether they respond well or whether they don't respond, we can call them either thermosetting polymers or thermoplastics polymers, okay? So just need to know the difference between the two. The main difference is thermoplastics are thermoplastics, so they can be melted repeatedly under heat. Thermosets or thermosetting polymers are set, okay, S-E-T, they're set, so they actually don't melt once they've been formed. We can't really expose them to a lot of heat and see that they melt, okay? And even if they do kind of show some give and they kind of melt a little, they can't then reform back into their original shape, okay? So that's basically the idea there. Okay, so thermosetting and thermoplastics. Thermosettings are set. They don't melt under the influence of heat. Thermoplastics melt much more easily, okay? So that's the main difference between the two. Some more comparisons between the two. Okay, if we think about something like, you know, the plastic cover that makes up a lot of game consoles like PlayStations, those are made of thermosetting polymers. What that means is if you were to take your beloved PlayStation and, you know, expose it to a lot of heat, it's not going to melt very easily. And this is really important, an important property, because when you buy a game consoles do overheat, okay, when you use them for hours and hours on end. And if it was the case that the PlayStation would just start overheating and melting, well, that wouldn't be very good for production purposes or even for consumers, okay, if you spend hundreds of dollars buying them. So that's one of the important reasons why a lot of our game consoles, a lot of our computer parts and computer CPU covers and all these kinds of things, they are basically made of thermosetting polymers that don't melt very easily under the influence of heat. Okay, whenever you have something that does overheat, it's very important to make sure you use a thermosetting polymer rather than a thermoplastic one. Another good feature of thermosetting polymers are that they're hard and rigid. So they don't just crumble, they don't just you know, wither away. They are hard and rigid and strong, okay? If anyone owns a game console, or, you know, you've got a CPU and, you know, you've got a fancy cover on it or whatever, those are hard and rigid substances. They don't break very easily. Even if you were to drop them, they wouldn't break in the same way that other plastics do. So some examples of real life items around us that are made of thermosetting polymers include doorknobs, again, hard and rigid, okay, do not melt under the influence of heat. Kitchen desktops, okay, think about it. When your mom takes the pot off the stove, sometimes she can't find the little oven kind of, what's it called? The little coaster that you put underneath before you put the pot on the bench top. So sometimes we do put hot things on the bench top. It doesn't mean that the bench top melts because the bench top is not made of thermoplastic. It's made of a thermosetting polymer there. Okay, Bakelite is another thing that we see in a lot of kitchen products, as well as melamine as well. Okay, so these are examples of things that can hold, that basically do not melt, or that can hold heat to some extent. Okay, they don't melt under the influence of heat. Obviously, though, if you were to, for example, pour like something really hot on your kitchen bench top, like lava, it's obviously going to start to char or turn black. It's not going to melt though. That's a different property. Okay, thermoplastics polymers though can soften. So if you've ever filled a water bottle and you've opened your tap or whatever, and accidentally there's hot water that's been coming in, you might notice your water bottle kind of shrinking, or kind of like almost like melting under the influence of the heat of that hot water. Okay, however, once that's kind of cooled down, you can kind of poke into it and you can kind of get it back to its normal shape. So that's what we mean by remolding something. Plastic also means that something is flexible. Okay, so in psychology, for example, when we talk about the brain being plastic, or the brain having plasticity, we say that that means that the brain is able to change its shape or change its structure over the lifespan. Okay, so plastic in general, even though we think of plastic as like plastic bags and plastic material, plastic actually means something that can be changed, or something that's flexible. Okay. Some examples of thermoplastic include plastic film, which is basically your Glad wrap or your cling wrap that you use in the kitchen. PVC, which is used in a lot of, you know, coverings and things like that. Buckets, okay, buckets, plastic buckets. A lot of toys are made of plastic as well. Water bottles, all these kinds of things are thermoplastics, okay? And you can see that they have those characteristics there. So just know the difference between thermosetting and thermoplastics. Okay. The formation of polymers. Look, we're not going to ask you to draw this in the SAC. It's more important for you to understand that certain types of polymers, we already know that our polymers are all made of carbon atoms. And sometimes those carbon atoms, what they do is they combine with other atoms to actually form a certain molecule of plastic. Okay. So basically what that means is we combine the two. So for example, polythene, we know about polythene in terms of polythene bags and that kind of stuff. So when we're talking about polythene is basically a polymer that consists of 2 carbon atoms and 4 hydrogen atoms. And you can see that reflected here. So we've got a double covalent bond between the carbon here. And then that forms 4 single hydrogen bonds or 4 single hydrogen covalent bonds carbon forms 4 single covalent bonds with hydrogen atoms there, with 4 hydrogen atoms. So we can see that that's reflected here. Okay. Again, we're not going to ask you to draw this out, so don't stress too much about this. Just showing you an example of how a polymer might form. Okay, polythene being an example of that. Okay, polymerization reactions generally occur under high temperatures and high pressure, which causes 2 or more compounds to join together, okay, and to create the many, many different molecules and types of plastics that we use in our everyday world. Okay, so that's basically what we're talking about when we're talking about formation of polymers there. Alrighty, so let's move on to uses of polymers. So the polymers are used for many different things. We've looked at some examples in the previous slides as well. Polymers are used for plastic bottles, they're used for tents, they're used for toys. If your mum or dad owns one of these jackets, these are polar fleece jackets. Polar fleece is actually a synthetic wool, which means it's not actually wool that's taken from sheep, it's actually man-made wool, which feels like real wool but isn't the real thing. Okay, synthetic wool is basically made or derived from PET, which is polyethylene terephthalate. Okay, that's basically a type of polymer there. That's a type of thermoplastic polymer. Okay, under a lot of temperature and a lot of heat and pressure, basically that is able to be sourced or is able to be turned into a piece of clothing that you can wear. Okay. So again, depending on how we put these products under a chemical reaction, the kind of energy that we expose them to, heat, and all that kind of stuff and pressure, we can actually change something like a bunch of plastic bottles and recycle them back into clothing. And you might have seen many clothing stores these days are doing that, where they say, okay, this jacket was made from recycled material. Okay, so that's the basic idea. So that's basically a practical use of polymers. So just know any one example of a real life object we use in everyday life that contains polymers in it, okay, which is basically everything we use. All right, so this is the summary. So polymerization is the name given to the process of forming a long chain polymer from smaller monomer molecules. So just remember, the smaller monomer molecules are our single units. Okay, they're the single units, mono meaning 1. So the 1 or the single units there. And these single units combine with each other to form a bigger unit, which is called a polymer. Okay, and a polymer is a larger, basically, molecule. Okay, elastomers are different because elastomers are basically more flexible. We can stretch them out like a rubber band, for example, and they will return back to their original shape. Crosslink polymers basically form lattices with a diamond-like appearance, and it's a lot more random and haphazard in terms of its arrangement. Thermoplastic polymers tend to soften under the influence of heat, so they respond very well to heat, whereas thermosetting plastics, remember, they're set, so they don't actually respond very well to heat. They won't melt or change if they are to be heated. Okay, so that's the basic summary. Like I said, it's all very much theory. There's no actual chemical equations in this chapter here. Okay, oh sorry, not in this chapter, in this spread. Okay, so that's the basic idea. Alrighty, so let's move on to the next spread, which is the most important spread probably for today. It's talking about how we can affect reaction rates, okay? So basically, there are many different ways at which we can influence the rate of reaction, and that's basically how quickly the particles in a chemical solution or chemical reaction collide with one another, okay? And we're going to learn about something called the collision theory, okay? And we are going to learn about how collision theory, or the rate of reaction of any chemical reaction that we do, can be influenced by increasing temperature, can be influenced by increasing the concentration of the elements you're dealing with, can be influenced by increasing the surface area, as well as can be influenced by stirring or mixing the reactants together to promote them to clash into one another. The basic idea, guys, is when we say reaction rate or rate of reaction, basically we're talking about the particles or the reactants that are in the chemical equation to the left-hand side of the arrow. Those are our reactants. How fast they basically collide with one another in a chemical reaction, okay? That's the basic idea. So it's all to do with the speed, how quickly, how rapidly, how fast those particles or those reactant particles or molecules collide with one another, okay? And there are certain conditions that need to exist in order for that to occur as well. So it's important to remember that a lot of the time, the rate of reaction does make a difference. If we have a chemical reaction that's too slow, sometimes that's going to be a waste of money, or it's not economic, because you've put on your equipment, you've put on your, your machinery, and you've turned everything on, but it's taking way too long for the reaction to take place. And so you're leaving that machinery or that equipment running, and it's not economic for you. You're wasting your money, you're wasting electricity there. So some reactions are too slow, okay? Some reactions that are too fast need to be controlled. For example, a very fast reaction is fireworks. Okay, if you're using a lot of fireworks and you're not using them properly or in the correct way, that can get out of control. That can get out of your hands, and you won't be able to control that, because the reactions that underlie, fireworks are basically very fast. They occur very rapidly. So it's important that we know about the factors that can allow us to best control the rate of a reaction, to ensure that our reactions are not too slow, but also not too fast to an extent that it gets away from us, so that we can't really put a stop to it. Okay, a really common example of another fast reaction that we still kind of can control is baking. Okay, sometimes we can control baking, sometimes we can't. For example, if you put a cake in the oven to bake and you've accidentally forgotten to turn the temperature a little low and it's really high, that cake will bake very quickly, even before you have a chance to be like, oh my God, I need to change the thing. It's already too late, it's already burnt. Okay, so again, even something like baking can get out of our control or can get out of our hands if we don't if we can't have much control over that. Okay, other reactions are slower, like rusting, for example. Metals don't rust in 24 hours or in just a few hours time. They take a while to rust. Okay, so if you leave an old car outside and you never drive it or you never look after it, and it's just constantly exposed to all the harsh climates and things, it will rust over time. Okay, because there are parts of the car that are made of metal that will be exposed to those oxides and will rust as a result of that and will corrode. Okay, so that's the importance of understanding why we need to be able to control the rate of reaction there. Okay, understanding that, we need to ensure that we've got the correct speed or correct rate of the reaction for what we're doing or for what we're dealing with. Okay, so what is collision theory? Now, just one second. I think I had a video for this one as well. So let me just, yes, I do. So let me just load that up, because I remember we showed this to last year's group and it was a good video. So I'll just load this up quickly. Okay, just give me 1 second. Okay, I'll just share the screen. Okay, I'll stop the recording here and then I'll share. Okay, so collision theory is this basic idea that in any chemical reaction, the atoms or the ions or the molecules or the compounds that are taking part in that reaction need to be able to kind of bump into each other, just like the boy and girl bumped into each other in the hallway, with enough energy, okay? And only then will the reaction occur. Remember, we can't have a reaction unless those two reactants are colliding with one another, okay? And basically, there are conditions for a proper reaction to take place. A reaction cannot take place, for example, if the reactants are not colliding at the correct position or in the correct orientation or angle, okay? If the molecules are not colliding in the correct angle in order for the two reactants to actually meet up, that's going to actually be an issue because they are not meeting up or they're not lining up with one another, okay? Also, just like the boy and girl needed to have energy to run down the hall, the reactants of the chemical reaction need to have enough energy to collide with one another, okay, in order to collide with one another. Now, as you can see in the second point here, some collisions don't result in a reaction because the molecules actually, rather than colliding with each other or kind of like, coming into contact with each other, they actually start to bounce apart, and that will then lead to no reaction. So the reaction can only occur if there is a collision. So reaction can only occur if there is a collision of the particles or the atoms involved in that reaction there. Collision, okay? So we need to understand that. And this is what the collision theory is, okay? The collision theory is this idea that in order for molecules in a chemical reaction to, cause a reaction or to increase that rate of reaction, they need to be able to be in the correct orientation, and they need to be in having enough energy. So in this example here, hydrogen iodide, can anyone remember what type of reaction this is before we go on? Where a big compound breaks down into the smaller constituent elements it's made up of. Anyone remember? It's just a name, the name of the reaction. I'll give you a clue. It starts with the letter D. Yeah, decomposition. Excellent. Good work. So a decomposition, this is an example of a decomposition reaction because a bigger compound or bigger element there, bigger compound breaks down into the smaller elements or the smaller constituent atoms that it's made up of, okay? This is the symbol for hydrogen iodide, and you can see it's been balanced because it's got a big 2 coefficient in front of it. So hydrogen iodide is a gas. Its molecules generally travel quite quickly, which means that it tends to have a pretty fast reaction rate or a high reaction rate. Okay, what that means is that the hydrogen molecules and the iodine molecules, basically, when they collide with each other, think of the hydrogen molecule and the iodine molecule being on separate sides of the hallway. The hydrogen molecule and iodine molecule are kind of running or kind of traveling or interacting very quickly with each other. Okay, they've got enough energy to do that. And they've got enough energy to do that. And when they collide or meet with one another, they collide in such a way that the angles are perfect. So the hydrogen atom is angled in a way that it completely or directly collides with the iodine atom. Okay, so they're always in the correct orientation or angle. They don't kind of bounce apart from each other. They don't kind of miss each other. They could directly collide. Just like the boy and the girl in the video directly collided with one another, hydrogen and iodine also collide with one another, which is what allows hydrogen iodide to have a very fast reaction rate when we combine these two atoms in the lab. Okay, so that's the basic idea. And all of this that we just talked about is represented in this diagram here as well. Okay, so that's the basic idea there. Yes, a catalyst will also help in increasing the rate of reaction, but we're not going to cover catalysts today. We cover catalysts in just a few slides in the last spread, which we're going to cover on Friday. But yeah, a catalyst does increase the rate of reaction there as well. Okay, so now that you know what collision theory is, and you know that reactants need to collide in order for the reaction rate to increase, we're going to look at 3 different factors or 3 different conditions that help in increasing the rate of reactions. Okay, again, repeating the rule, to increase the rate of reactions, we need to increase the number of collisions. Okay, the number of collisions between the reactant particles that are in that experiment or in that chemical reaction that we're looking at, okay, between the reactant particles. Okay, so how can we do this? We can do this by increasing the surface area. We can do this by increasing the concentration of the reactants that are involved, which means choosing a stronger concentration, or we can do this by increasing the temperature. So some chemical reactions happen faster under the influence of heat, for example, compared to being in a very cold room. So that's what we're really looking at now. Okay. So the first one is increasing the surface area. This is a really something we do every day. If you think about it, if you've ever seen like a sugar cube, okay, if you've ever seen a little cube of sugar that looks something like that, basically when you've got a cube of sugar and you put it into a cup of coffee, it is not going to melt very quickly. It's not going to kind of melt straight away into that coffee. However, when I take a spoon of sugar and I put that into my coffee, it dissolves straight away. Okay. The reason being is that when you've got something in a powdered form, whether that's sugar, whether that's a piece of metal that you've crushed into powder form, basically you've got a larger surface area to work on. You've got more surface area to which the reactants can be exposed, okay, compared to having large size chunks or bits or cubes of that same sugar or metal that we're talking about. Okay, this is why in some reactions or some experiments or practice in the lab, rather than taking a chunk of a metal like magnesium metal, we actually, we crush that or we turn it into a little powder before we use it, because we know that that will improve the efficiency and the speed of the reaction there. Okay, you can see that here, that when you've got larger marble chips compared to smaller marble chips, it generally takes more time for the larger marble chips to actually react in that reaction. So the reaction becomes a lot slower in that sense. Okay, so when we're talking about magnesium metal and hydrochloric acid, just as an example, rather than taking a big chunk of the magnesium metal, like I said before, cutting that magnesium metal into smaller pieces can actually help us to increase the surface area. So the reactants that are involved in that reaction, in this case, hydrochloric acid, actually has a larger space on which it can work or on which it can collide, okay? So larger surface areas always lead to a faster reaction rate, okay? Because larger surface areas lead to more collisions between the reactant particles there. Okay, so that's the basic idea. The larger the surface area is, the better will be our percentage of successful collisions there. Okay, so that's the basic idea behind increasing the surface area. Increasing the concentration is basically saying that when we've got an example of, a solution, or when we've got, for example, hydrochloric acid, if we're using hydrochloric acid in a chemical reaction, basically what we're doing is we're using hydrochloric acid along with another metal and just seeing how they react, okay? Now, depending on whether you use concentrated, which is pretty intense or high strength hydrochloric acid, or dilute, which is the weaker kind of hydrochloric acid there, your reaction will be different. When you've got more concentrated solution, you've actually got more particles, as you can see in this diagram here. There are more particles of that solution, of that hydrochloric acid in a concentrated version of hydrochloric acid compared to a dilute beaker that's filled with hydrochloric acid. Think about cordial. When you pour cordial into a cup, there's more concentration when you pour more cordial mixture into it. That's because there's more cordial particles in the glass compared to water. Okay, in a dilute solution though of hydrochloric acid, it's less concentrated, and you can notice that it's a lot lighter in color. It doesn't look as intensified or as concentrated as the dilute version, as the concentrated version. Okay, and that's because you've got less particles, as we can see here. There's less particles of the hydrochloric acid in the dilute beaker that's got the dilute hydrochloric acid in it, okay? The more particles you have, or the more concentration you have of a specific element or compound there, the faster will be the reaction rate, because more collisions will occur. You've got more particles there that will collide, okay? So if you think about it this way, if we're linking back to the analogy, if the girl is running down the hallway, but there's so many people running down towards her, she will end up colliding with somebody, okay? The chance of her colliding with someone will almost be 100%. It might not necessarily be that boy, but it might be someone else. And that's because there are more people in the hallway. In the same way, when you've got a concentrated solution, there are more particles in that particles of hydrochloric acid in that beaker. So the collision is more likely to occur as a result of that, because as this picture says, there are a greater number of particles that are available to react. Okay, and that increases the rate of reaction by increasing the collisions between those particles. Okay. Oh, haven't I changed? Oh my goodness, why didn't anyone tell me earlier? Okay, you should have told me, guys. I forgot to change the screen. I didn't even realize, and I'm just explaining. Okay, hopefully everyone can see that now. Okay, tell me earlier next time. Oh my God, I feel so silly. I'm just explaining without even sharing the screen. Okay, what we went through, guys, those of you who didn't see the slides, I just talked about what a collision theory is. I just talked about an example with hydrogen iodide there. Okay, and then I just talked about increasing the rate of collisions, and we said that in order to increase the rate of reactions, you've got to increase the number of collisions. Okay, so the more the reactant particles collide with one another, automatically that's going to increase our rate of reaction there. Okay, make the rate of reaction faster, essentially. Then I started talking about increasing the surface area, which basically indicates, basically indicates that when you take a big chunk of metal or a big cube of sugar and you make that into a powdered form, it's a lot easier for that reactant to then increase the rate of reaction in that chemical equation or chemical reaction that we're dealing with. Okay, so for example, magnesium metal, rather than taking magnesium metal as a big chunk, what we're doing is we're actually making it into a powder, and that allows the magnesium metal to have more surface area or more space. Okay, and when there's more space, the hydrochloric acid can more easily act on that space, okay, in order to have an effect there. And the particles of hydrochloric acid will more easily collide with the particles of magnesium metal because you have a larger surface area on which you're going to work on. Okay, that's the basic idea. So that's basically looking at increasing the surface area. When we're looking at increasing the concentration, I was just talking about this idea that when you've got more particles of a particular compound or a particular acid or whatever it is in a solution, the simple idea that there are more particles increases the risk of a reaction occurring. So when you've got more particles, the collision rate will be faster. Okay, just think about the boy and the girl running down the corridor that we saw in that video. Okay, when the girl and the boy are the only people running towards each other in the corridor, they will bump into each other if they're at the right angle and they've got enough energy to run towards one another. But sometimes what happens is that they might not necessarily bump into each other because there's one of each of them. However, when you've got a concentrated solution, the girl's running down the corridor and there are multiple people running towards her. So there's always going to be a chance that she's going to bump into those multiple people. Okay, so when you've got multiple particles or dissolved particles in the solution, we say that that's a concentrated solution. Okay, that's going to be more likely to elicit a faster reaction rate compared to a dilute solution where there are less number of particles in that same amount of solution there. Okay, and you can see that we can always tell whether something's concentrated or not by looking at the color of the solution. Concentrated solutions are always darker in color, whereas dilute solutions are always lighter in color. Okay, so that's important to remember. Also think about it with cordial, for example. When you pour cordial into a cup, if you just pour a lot of cordial, your cordial will be darker in color. If you add a little bit of cordial and a lot more water, it becomes a lot more diluted. Okay, which means that now there's less cordial particles in the glass and there's more water particles in the glass. So that's kind of another comparison there. Okay, the more the concentration is, the more reactant particles will be present, and thus the more likely it is that the reactant will collide with the other reactant in the scenario there. Okay, just remember that rule. High concentration means more collisions. Okay, so moving on to the next one, just showing you guys an example of using the same type of acid. This is a very simple reaction that takes place using the same sulfuric acid, mixing it with sucrose, which is just sugar. And how we see the difference in reaction. You see in the first picture here, we're putting concentrated sulfuric acid plus sugar. And in the second beaker here, we're using dilute. So this one's got more particles of the sulfuric acid there, whereas the second beaker has less particles. Yeah, the second beaker is diluted. So this is our concentrated one. Okay, now when he pours the concentrated sulfuric acid into the beaker with the sugar in it, look how fast it reacts. At 60 seconds, the product there has literally exceeded the size of the beaker. Okay, we see a lot of smoke forming, complete color change, a complete charring there that's occurred as well. Okay, and that only took 60 seconds. But in that same 60 seconds, the dilute sulfuric acid basically stayed more or less the same. There was no change. Okay, the reason that this happened to the concentrated sulfuric acid beaker is because when you've got more concentration, or when you increase the concentration, that increases the rate of collisions. And when you increase the rate of collisions between the sulfuric acid and the sugar particles, you're increasing the rate of reaction, making it a lot faster for the sugar and the concentrated sulfuric acid to show such a dramatic reaction as this, as we see in the third picture here. It only took about 60 seconds, and already at the 15-second mark, it was already starting to show a clear change in reaction and a clear reaction rate. That was very fast and rapid there. Okay, so just showing you a visual comparison between the two. Okay, when we increase the temperature, that can also lead to a difference in terms of rate of reactions. Okay, so when we heat up, for example, a solution, that can actually lead to more kinetic energy being present. That causes the particles to collide faster. If you've ever made dessert or something like that, and you've had to make like a sugar syrup or a simple syrup to pour on top, you often heat sugar in a saucepan with some water, okay? And when you do that, as the sugar starts heating up with the water in the pan, it actually starts to boil a lot quicker and the syrup starts to form a lot quicker, okay? You would never be able to achieve that same consistency or that same kind of product by just putting the sugar in cold water and waiting, okay? Because when we put sugar in a hot substance like boiling water, it starts to get more kinetic energy and starts to collide a lot faster, okay? So that's the basic idea, that when you heat up a particular solution, that particular atom or particle has more kinetic energy. And when it's got more kinetic energy, the particles that are in that solution travel a lot faster. And what that looks like visibly to us is that the rate of reaction happens very fast, okay? So the particles will collide faster with each other because of that kinetic energy that they have, and that will increase the overall rate of reaction. So in front of us, we'll see a very fast reaction taking place. Okay, this is just some diagrams to show you how kinetic energy plays a role, okay, in terms of increasing the rate of increasing the rate of reactions, and how increasing the temperature of the reaction can lead to a higher frequency of collisions, as well as leads to a higher level of kinetic energy that's kind of absorbed by those particles there. Okay, so that's the basic idea. We're not going to ask you to draw these graphs out. These are just for your own understanding there. These aren't even from the book, but they're just for your own understanding. Okay, so again, increasing the temperature increases the kinetic energy of those particles, and this increases the frequency with which those particles collide with one another. Remember, collide faster means faster rate of reaction. Just always remember that rule, always link everything back to that rule. Okay, and the last one that we're looking at for today, guys, which is another type of way in which we can increase the rate of reaction, is stir and mix. Stir and mix is a really, really simple concept, basically talking about this idea that, one second. Okay, basically talking about this idea that when we have a solution or we have reactant particles in a solution, sometimes when they're just sitting there, that doesn't really help in terms of, speeding up the reaction. So in order to actually speed up that reaction, we actually have to go in and give it a good manual stir and mix. That's basically what stir and mix is, okay? When there are fewer particles of those reactants, sometimes the reaction rate slows down, okay? Sometimes we don't have a lot of magnesium metal to work with, so we're only working with a little bit of magnesium metal there, okay? If that's the case, we can actually manually speed up the reaction by going into the beaker and just stirring and mixing the solution. So stirring and mixing those two reactants manually, and that can actually allow more reactant particles to take place there, okay, or to operate there in that particular reaction, okay? So in a magnesium and hydrochloric acid reaction, when you stir the solution manually, like just go in and stir and mix it up in the beaker, what that does is any products that are formed like hydrogen gas will actually be swept away, and more of that hydrogen atom can actually now react with that magnesium surface of that magnesium metal. Okay, so stirring and mixing is a more manual way in which we can accelerate the rate of reaction by causing or forcing, in other words, we're forcing the two particle or the reactant particles to collide with one another. So we're going in and we're kind of giving that a hand in order to speed up that reaction. Okay, so that's the basic idea. And you can see the difference between a not stirred beaker and a well-stirred beaker. In a well-stirred beaker, you can see that there are more particles of the hydrochloric acid as well as the marble chips that have kind of formed there, okay, because of the manual stirring and mixing. Alrighty, so that's basically covering 4.8. If there's any questions you guys have about 4.8, let me know. 4.8 is a really important topic. Just if you don't understand how increasing the temperature allows for an increased rate of reactions, just let me know. As you can see, there's not many chemical equations in this spread. These two spreads that we covered today were very much theory-based, okay? So just make sure you understand the theory. And if you don't, just send me an email and I'm happy to explain it some more. So what I'm going to do is I'm going to stop the recording here.